Hey everybody, it's Mr. Slomka again with another video lesson. Today's lesson is going to be on section 9.4, which is about mathematical induction. Mathematical induction is a way of proving a mathematical fact, and it is a new and very, very different way of proving things than what you might be used to. It's a very, very helpful skill for math courses that are after calculus. So if you plan on extending your math career a little bit further than just your average calculus class, this will be a very, very beneficial skill. We're going to look at some that have to do with sequences and series, because that's what we learned about in chapter 9. So let's take a look at this first one that we have right here, and then I'll talk about this box that we have up here in a little tiny bit. So let's take a look. It says, does 5 plus 7 plus 9 plus 11 plus 13, those numbers seem to be following some kind of pattern, and that pattern is written out for you right here, plus ... 3 plus 2n. So what we have is we have this very, very long list of numbers, and we get so lazy that we're not going to write them all down, and they all happen to follow this pattern right here. Is this all equal to n times n plus 4? And so what we're going to do is we're going to see if we can prove that fact. Now the first part says show work that could convince someone. So what you want to do is you just want to try and convince someone, and usually that someone is yourself. So what we're going to do is we're going to try and take a look at a couple of these things, and we're going to see if it actually works, or in a way that we can convince ourselves. So let's begin real easily. So what I'm going to do is over here we're supposed to be adding terms together, and what I'm going to do is I'm just going to add the first term. So our first term over here on the left side is a 5, which is great. And on the right side, if I wanted to know what the first term is over here on the right side, then what I would do is I would have to type in a 1 for n. So it would be 1 times 1 plus 4. Well, that works out pretty well because 5 is going to be equal to 1 times 5. 5 is equal to 5. That's pretty good. Now, sometimes a 1 is a really easy number to work with, so it might be a little bit of a fluke. Let's look at a little bit more advanced case. What about two terms? So if we use the first two terms, that is 5 plus 7. If we add those two guys up, it should be equal to the right side, but you should put a 2 in there instead. So that would be 2 times 2 plus 4. If you do those, 5 plus 7 is going to give you 12. And over here on the other side, 2 plus 4 is 6. 6 times 2 is also 12. All right, cool. That's working out pretty well. You could even do it for 3 terms if you want. 5 plus 7 plus 9. And that should be equal to 3 times 3 plus 4. And not surprisingly, this one works out as well. And you end up with 21 is equal to 21. So at this point, after you've done 3 terms, most people are pretty convinced. They're like, oh, okay, I get it. If you just keep on adding terms, the number gets bigger and the left side's always equal to the right side. Cool. But mathematicians need a little bit more. You need to have this robust proof to show that it actually works, not just, oh, the first couple look good, so it's good enough. So here's what we're going to do. What we're going to do is we're going to take a look at these 4 steps right here. First step is going to be to set up one of these easy cases. And most of the time, the easiest case is when n is equal to 1. And we want to make sure that the left side looks like the right side, kind of like what we did right over here. It doesn't always have to be 1. You can pick another easy small number, but 1 is usually the easiest and smallest, so we go with that. Then what you're going to do is you're going to set up an assumption. Now, this assumption is going to say that n is equal to k is true. So you're making up your own number k that is supposedly true, so that the fact is true. Then what's going to happen here is that you're going to then let n equal k plus 1, and you need to show that that case is also true. Basically, what you're doing is you are setting up a line of dominoes. Like we did here. We set up the 1 domino, and then the 2 domino, and then the 3 dominoes. And every time we set up our dominoes, we gave them a push, and 1 domino pushed against the other, and the other, and the other, and soon enough they all fell over. That's what you're doing here. You're setting up 1 basic domino, and then you're setting up k dominoes, and then k plus 1 dominoes, and if they all fall down, then you know you're in good shape. So that's kind of what's happening. It's this proof by this never-ending loop. Okay, if this number works, then the next one's going to work, and if that number works, then the next number works, and if that number works, then the next number works, and so on and so forth until you get to infinity. So that's a really, really crazy way of thinking about things, and that's why we're going to take a little extra time to work on these over the next couple days. Let's take a look at our next example that we have right here. So this is the exact same problem again, except this time we're going to prove it by induction. So to begin with, we're going to use some words, and I want you to use pretty much the exact same words that I'm going to use for a couple of reasons. One, I know that they work very, very well because this is the same wording that I used when I was in university, and 2, they are the most boiled down and essential wordings that I know of. So there's no extra words in there. And I know that you guys really like to do things as efficiently as possible. And so this is it. There is no shorter way. So if you're like, oh, well, I'll shorten this or I'll shorten that. No, you won't, because it will not satisfy the induction proof. So you have to use these words or more, but I doubt you want to use more. So let me show you what we're going to do. To begin with, here's some of the first words that you need to use. What we're going to do is we're going to write down let n equal 1. And one of the phrases that's going to pop up a lot is the phrase such that. So we're going to write down such that. And usually when you write down a phrase such that, you usually show some work after that. So with the such that, what you're going to do is you're going to go up to your equation and you are going to create the 1 case. Now you can do it in the same way that we did, and you can pull the 5 out. And so you can say 5 is equal to, and then put a 1 into the right side over here, which would be 1 times 1 plus 4. And then you can simplify and you'll get 5 is equal to 1 times 5, and 5 is equal to 5. Perfect. Some people, if you want to be a little bit more thorough, and I'm not saying you have to be, but if you want to be, what they'll do is instead of just cheating and pulling out the first term, they'll create the first term using this guy right here, and that would be 3 plus 2 times 1. And then they set that equal to this guy over here, which would be 1 times 1 plus 4. If you do it this way, you still end up with 5 is equal to 5, and that works out fine, but it's just a little bit of a different way to do it. So you can cheat and pull it from right here, or you can use the formula to get it right there. Either way, you end up with 5 is equal to 5. Both of these things are perfect. That's exactly what you need it to be. So what you could then get to do is since n is equal to 1 is true. So what we have to do is we have to explain what we just did. We just showed that n is equal to 1 actually worked. 5 is equal to 5 means that it's true. What you're going to then do is you are going to create this second part that is right here. You're going to set up the n is equal to k part. Assume, this is another popular word, assume n is equal to k is true. And I'm going to use my favorite phrase again, which is going to be such that. Okay, now this one's going to require a bit more writing. Let's take a look what the writing is going to look like for this one. So now for n is equal to k is some number, and we don't know if it's really big or really small. So here's what's going to end up happening. You're going to not just be able to pull out the first couple terms like we did here, not just the 5, the 7, and the 9, but you're going to have to write out everything that you see here, except now that n is equal to k, you're going to replace all the little n's with k's. So you're going to write the whole thing down. So it's going to be 5 plus 7 plus 9. Now, if you want, I'll give you a little cheat. You don't have to write down all these terms. So you can write down a couple, and then you can put your dot, dot, dot in, and then you can write down your, instead of 3 plus 2n, it's now going to be 3 plus 2k is equal to k times k plus 4. So there is your new piece right there. Now this is a very, very exciting piece right here. This piece is the only thing that we are really going to be able to fall back on and know, or at least assume, that it is true. That word is extremely powerful right there, and that means something. Specifically, it means that this equal sign works. All the other equal signs that we're going to see later on are questionable. So it's like an equal sign, and it looks exactly like it, but we're just not sure if it actually works the same way. So we just need to prove it. And this one is assumed to be true, so it works. So now, next piece, the third to last one, the biggest one. What we're now going to do is we are now going to let n equal k plus 1. And then I'm going to use that such that again. Now I'm going to copy down the same line of text all over again, except for with my n's, I'm going to now replace it with not just k, but k plus 1, which is a big deal. A lot of times what's helpful for this k plus 1 case is if you use a couple extra parentheses so that you see the k and the plus 1 working together, not as two separate terms. So I'm going to have my first couple terms, then my dot, 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 and then what I'm going to do is I'm actually going to put a little gap right here, and I'll explain why I have this gap right here in a little tiny bit, and then I'm going to use this part right here. 3 plus 2n is now going to be 3 plus 2 times k plus 1. There it is right there. There's the term. All right, then the equal sign after that. And after the equal sign is going to be this guy right here, except I'm going to use k plus 1s. So on the outside, I'm going to have a k plus 1 in parentheses. And then on the inside, I'm going to have my k plus 1 plus 4. And that's going to have its own set of parentheses right there. Take a look at that guy. This is it. This is the most critical step right here. This is the most helpful step right here. This is the most critical step. So it goes real easy up here, very helpful, and then most critical. Let's see if we can fix that most critical step right here. So here's the thing. What I have right here is I've got this very long list of terms all the way up to the k+1 term. Now, it's such a long list of terms that it's hard to really work with. I really don't know much about it, and I can't really do anything with it right now. So what I need to do is I need to try to relate this list of terms back to something that I already know about, which is this guy right here. If I can do that, then maybe I can simplify it a little bit. And the goal is to make this left side, this extremely long list of terms, look exactly like the right side, which is only a small little set of polynomials that you can simplify very, very quickly and easily. So this part is small and easy, and this part is huge, or maybe not, and we need to make them both the same. So let's see if we can do that. So on this left side right here, here's the one fact that I really, really know about. We're starting off with 5, 7, 9. That's a familiar start. And if you take a look right above it, this one also starts with 5, 7, 9. Now the problem is that this list down here does not go goes up all the way to 3 plus 2k plus 1. That is one term bigger than this guy right here. This one only goes up to 3 plus 2k. So k plus 1 is a little bit bigger than the k term. That means that if I wanted to write in one extra term in front of this guy, that term right there, the term right before the last term, I could. And it would happen to be 3 plus 2k. Whoa, that's crazy. The reason why that's crazy is because this chunk right here I know a lot about. Starting at the 5, 7, 9 and going all the way up to the 3 plus 2k, that's equal to something. 5, 7, 9, all the way up to the 3 plus 2k, it's equal to this chunk right here. I can replace this whole chunk that is very, very long with a nice small little bit. K times k plus 4. Awesome. Then I still have my plus sign right here, and I still have my 3 plus 2k plus 1, and I have everything over on the other side of their equal sign, which is going to be k plus 1 and k plus 1 plus 4. That got it so much smaller. We went from a list of terms that was so long that I didn't even know how long it was. Now I have a couple of small little polynomials, a bunch of distributive property opportunities, and I can simplify this down. So once again, if we can make the left side look like the right side, then we'll be done. So let's see if we can FOIL this guy out a little bit and see what it looks like. So over here on the left side, you've got k times k and k times 4. So that's going to be k squared plus 4k. Then you've got this 3 right here, and he's not really going to do too much. So we're just going to hold on to that guy right there. And you've got a 2 that's going to get distributed to give you 2k plus 2. There are some terms in there that I will be able to combine together, but not just yet. Let's look at what's happening over on the right side. On the right side, you can do a couple things. You can combine the 1 and the 4 together, or you can just start foiling right away. It's up to you. I think I'm going to combine the 1 and the 4 together, which is going to give me k plus 1 and k plus 5. There. Okay, back to the left side over here. I can simplify some stuff over here. I have a k squared term, which is going to be good. I've got a 4k and a 2k, which is going to bring it up to 6k. And I've got a 3 and a 2, which is going to be a 5. Awesome, that's looking pretty good. Over here on the right side, k times k is going to give me k squared. Great, that looks good. K times 5 and k times 1 is going to be 6k. Awesome, that looks really good. And then lastly, 1 times 5 is going to be 5. Great. Left side looks like right side. We started off with our first step, making the left side look like the right side. In our second side, we assumed that the left side and the right side were equal to each other. And in our third step, we made it. We forced the left side and the right side to look exactly the same. Now, a lot of times for the ending of these problems, it is difficult and different and unique to make the left side and the right side look the same. Use all of your algebra skills that you have available to you to make that happen. Make the left side and the right side look the same. Okay, now let's finish off this proof. We're almost done, and so we only have a couple more words to write in. Now I'm running out of space down here at the bottom, so I'm going to bump up here to the top right-hand corner of my page, and I will finish it off here. So now the ending words are also very, very specific. There are some very popular mathematical terms that we're going to use here. First one is therefore by induction. Therefore, very popular in mathematical proof. Therefore, by induction. So that's the technique that we used right now. We just used the induction technique, which is one of 3 different ways to make or create a proof. Therefore, by induction. Now, for our very last time, what we're going to do is we're going to go back up here and we're going to copy this piece right here. But this time we're going to copy it exactly how we see it with the n variable. So that's going to be 5 plus 7 plus 9 plus ... all the way up to 3 plus 2n. And that's going to be equal to n plus 4. n plus 4. And we're going to finish it off with a little tiny bit more. Is true. And don't forget, just like last time when we made a proof, we have to create a mark of triumph. And so we're going to do that right here. I like the box. I like check marks. I like the Triforce. I like the Deathly Hollows. Whatever you like is fine by me. Just give me some sort of mark of triumph so I know that you are done. And that is your really first induction proof, which is great. That's an awesome proof right there. Let's try another one. So on the back side, what we're going to do is we're going to try to make it a little bit tougher, but not all that much tougher. So what we're going to do is we're just going to change the way that it looks originally, but we're just going to turn it right back into the thing that we just worked on last time. So here's the problem right here. It says use mathematical induction to prove. Now here's the thing. That's sigma notation. And so you might be like, oh, I hate sigma. That's not my favorite thing in the world. Yeah, I get it. There are lots of people who don't like sigma, but it does represent addition. So what you're basically doing is you're doing another addition problem, just like the last one. So let's see if we can set it up so in a way that you might like it a little bit more. So here's what I'm going to do. I'm actually going to write out the first couple terms, and then I'm going to put a ... and then I'll put my last term in, just like our last example problem. So let's take a look at the first couple terms. I'm going to start by putting some 1s in here. So that's going to be 1 times 1 minus 1, and then my next term would be with 2's in there, which would be 2 times 2 minus 1, and then I would have 3's in there, which would be 3 times 3 minus 1. Now you don't have to write out a bunch of these, just a couple to make yourself feel comfortable. For the rest of them, you can skip with a ... and then I'm going to go to my very last term. Up here at the top of my sigma, it says that I need to go up to n, so my next one's going to be n times n minus 1. There you go. Now it's written out as a list. So you can simplify that list, or you can leave it exactly how it is. It doesn't matter to me, but that list is going to be equal to n times n minus 1, n plus 1 over 3. This is the thing that we now have to prove. If we prove this is true, then we're essentially proving this is true, and that's perfect. So let's see if we can do that same way. We're going to go through the same exact steps. So now, once I mentioned before, some people like to simplify these, and if you want to do that, that's totally fine. This first one is a 0, and the second one is a 2, and the third one is a 6. That's totally fine. And if you want over here, that's n squared minus n, but if you don't want to simplify them, you don't have to. That's your choice. So you can do whatever you want. Let's start with our proof. So now our proof is going to be following the same steps that we used last time. So the first one is let n equal 1 such that is the cue that you are going to now start showing some work. So over here we're going to use our 1 term, which is 1 times 1 minus 1, or you could just cheat and use the 0. And then over on the right side, this is where the most important part is going to be. That is going to be 1 times 1 minus 1, 1 plus 1 over 3. Now once again, just like always, left side and right side need to look the exact same. So let's see if we can do that. Over here, that's going to be a 0 times 1, which is going to be 0. Over here, this guy is going to be the 0, and so once again, everything's going to go away, and you end up with 0. Totally works. So, now our next set of words now. Since n is equal to 1 is true. So we now know that n is equal to 1 is true. We are going to make an assumption. Assume n is equal to k is true, such that And now what we're going to do is we're going to create our n is equal to k case. So for n is equal to k, you need to write out the whole thing with the k's in there. So that means you have to write out the first couple terms, and you have to write out this guy with the k's in it, and this guy with the k's in it as well. So let's take a look at what that's going to look like. So you can write it out with these guys right up here, or with these ones down here. It's your choice. I'm going to pick the bottom row. So I'm going to write it as 0 plus 2 plus 6 plus ... all the way up to... And I'm going to use this guy right here. I actually kind of like this one a little bit more. K times k minus 1. And then over on the other side, that's going to be equal to k times k minus 1 and k plus 1 over 3. So this is the fact that is now true. That true right there is a very powerful word in the world of induction, because that true means that you have a powerful fact, and we're going to do our very best to use this powerful fact to do some good. So then our third and final, or no, not our third and final, but our third set of words that we're going to use is let n equal k plus 1. So this is going to go right up here for our next step right here. Let n equal k plus 1. And then I'm going to use my favorite phrase at this point, such that, and now that means we're going to show some work. So our such that. Let's set up our k plus 1 case. So we're going to start off with our first couple terms, which is our 0 plus 2 plus 6 plus ... And now in this one, I'm going to leave that gap that I was talking about last time, and I'm going to go all the way up to k plus 1. So last time it was k times k minus 1. Now it's going to be k plus 1 times k plus 1 minus 1. That can be a little confusing. There's a lot of ones, and it's going to get worse. On the right side, it gets even worse. So on this right side, it's going to be nutty. First one is going to be k plus 1. Then you have n minus 1 is going to be k plus 1 minus 1. And then your last one is k plus 1 plus 1. Oops, plus 1. There you go. And then lastly, it's all over 3. Some people, what they like to do is they say, oh, Mr. Slomka, can I just do the plus 1 right away, or the plus 1 minus 1 right away? Yeah, you don't have to write it down. But I will warn you, there are other people out there that if they don't write it down, they mess it up. And so I don't want you to mess it up. Make sure that you get it down. So I'm one of those people who needs to write it down, so I have written it down. Okay, so now as I had mentioned, what we have right here is we've got a gap, and this gap is a very, very important one. We need to fill in that gap. The reason why is because I've got this long list of terms, and I need to set it equal to this one compact fraction, and so it's very hard to work with such a long list of terms, especially if you can't see all the terms. So I need something to work with, and the only thing that I really have is I have this fact right down here that also happens to involve a long list of terms. Now it's true, this long list isn't as long as this list right here. In fact, this list is one term longer, and so if you went back a term from the k plus 1 term, you could go back to the k term, which happens to be k times k minus 1. That term sits right there. Almost the last term, but not quite. This chunk of facts right here, that is something that I know about, and I can use my fact that I know about that to help me out. Specifically, I know that if I start at 0 and I go all the way up to k times k minus 1, 0 all the way to k times k minus 1, it's equal to this fraction. So what I can do is I can replace this whole chunk with the fraction k minus 1, k plus 1 over 3. Awesome. That's so great. Now my list is not so long. There's a fraction. I also have this chunk right here, which I'm going to need to deal with. K plus 1. And if you want to start simplifying a little bit at this point, you can. And the whole thing is supposed to be equal to this fraction right here, which I'm also going to start simplifying as well. So I'm going to start with my k plus 1. Then k plus 1 minus 1 is just going to be k. And k plus 1 is going to be k plus 2. Take a look at that. Awesome. Okay, so now what a lot of people are going to say is, oh, I know what to do now. I just need to FOIL. And you're right, you could. You could do a lot of foiling over here and over here and over here, and you could make them look the exact same. But I don't have that much space, and I don't really know if I want to FOIL all that much. So as I had mentioned last time, use all of your algebra skills, not just the distributive property. So here's something else that I'm noticing. I'm noticing that I see a lot of denominators of 3. And that's pretty cool. But this guy does not have a denominator of 3, so I would like to create a denominator of 3 for him. Here's the other thing I'm noticing. I'm noticing that I have a lot of common factors. And so I'm seeing k's, and I'm seeing k plus 1s. And so I'd also like to use that as well. So let's see if we can use a different technique for this one. Could you FOIL it all out? Yes. It'll take a little bit of time, and you might make a mistake or two because it takes so many times of foiling, but it's very doable. So that is totally fine if you want to do it that way. But I'm going to try and show you a different way just because this is the notes and we have to diversify things. So let's do that. So the first thing I'd mention is the denominator. I see denominators 3 over here and over here. That's promising, but we need more. So I'm going to create another denominator over 3. Now, if you do that, you can't just put it on the bottom. You have to put one on top as well. So I'm going to do that as well. So here's denominators of 3 on top and on bottom. Here's the other thing I noticed. I also noticed that I've got those common factors, k and k plus 1. So what I'm going to do is I'm going to start factoring out some common factors in the numerator. So let's see what happens when we do that. I'm going to create one big mega fraction, and this mega fraction is going to be over 3. I'm going to take out the k and the k plus 1 from the first and the second. So I'm going to have my k and my k plus 1. What that's going to do is from the first term, if I factor out the k and the k plus 1, I'm left with k minus 1. And from the second guy over here, if I take out the k and the k plus 1, I am left with k, just the 3. So we're going to have our 3 right there. This is all supposed to still be equal to the right side. And you need to write down that right side after every step, even if you don't do anything to it. And in this case, I am not doing anything to the right side, except trying to match it. But I still need to write it down. So there's your left side and right side. If you look closely, you'll notice that they're getting very, very similar, dangerously similar. Specifically right here, this is the only one that looks a little strange. K minus 1 plus 3. Well, minus 1 plus 3 is going to turn into a 2. And so all of a sudden you end up with k plus 1, and k plus 2 over 3. Awesome. That happens to be the exact same 3 terms in the numerator that we have over here in this numerator, and the denominators are definitely the same. Now the order is slightly different. Over here it is k plus 1 first, and then it's the k, and then it's the k plus 2, but that doesn't matter because it's multiplication. So as long as the left side looks like the right side, you are good to go. So that's really, really great. And finally, to finish this guy off, you still need to finish it off. So that means we're going to end our proof. Therefore, by induction, and then you're going to copy down this piece right here, and you need to say is true. So I'm running out of space right here, so I'm going to cheat a little bit, and I'm going to add on a little extra extension to my problem right here. So let's see if we can write it in. So here's my last step that I just created right here. So I'm going to fill it out once again. Therefore, by induction, and we're going to copy down the original problem exactly how you see it. No k's this time. It is going to go exactly how you see it. So you do have to write down the sigma notation, although we really didn't do anything with it, and that is okay for some people. They don't like sigma notation and they'd rather avoid it, so they are okay with only having to write it down the one time at the end. And we have to write it down, and then we have to tell about it. Then this fact is now true. So we're going to say is true. And then you have to make your mark of triumph. So whatever mark you would like is fine by me. And so that lets us know that we now have a perfect proof, and it is all set and done. All right, last one that we're going to take a look at right down here. So once again, this is looking slightly different, but it is very, very much the same thing. And I'm going to help you set it up, and then I want to see if you guys can finish this guy off on your own, because you're going to need to try and practice one on your own. So let's take a look at what it says. It says, consider the series, and we have -3 plus -11 plus -19 plus ... Now I wrote this one in a little bit of a weird way. I did put pluses and the negatives on there, and I did that just so it looked a little bit more similar to what we're used to. I could have -3 minus 11 minus 19, but I wanted to remind you that it is addition, so we are doing addition problems. You won't likely see those plus signs ever again, but it's our first time, so I'm putting a little extra into them. So what I want to know right here is I want to write an explicit rule for the nth term of the sequence. So now an explicit rule, if you remember, are things that we had at the beginning of chapter 9, and we had 2 of them. We had an arithmetic one that used a common difference, a d value, and we had a geometric one that used a common ratio, an r value. So first thing we might need to do is figure out which one we need to use. if you look at these numbers, they're getting more negative. But they're not getting more negative very fast. There's only a slight change between each one of them. And that's because if you start subtracting them, you start to get the same answer every time. And that same answer is -8. That is a common difference, meaning that our arithmetic sequence or formula would work out really great. The formula is A1 plus n minus 1 times D. And I'm going to use my A1 value, which is right up here, -3. And I'm going to use n minus 1 as my variable, and then D is that difference value, which is -8. A little warning on these ones, when you use negative numbers at the back here, put it in parentheses, please. That way it doesn't look like subtraction, it looks like multiplication. So there is our explicit rule for the nth term. Next part, it says create an equation for the sum of the first n terms. So for our sum formula, what we're talking about is we're talking about adding these terms together. Now we have an arithmetic sum formula as well. And now that sum formula looks like this. It's going to be n over 2 times a1, your first term, plus an, your last term. So now this one's going to get a little bit of a twist. So we're adding up n terms right here. So we're going to actually start off pretty much the same, n over 2. Then a1 happens to be your first term, which we know is -3. And then here's where things get a little tricky. an is supposed to be your last term, but I don't know what it's supposed to be. It's not the -19. See that dot, dot, dot? That tells you keep going. And that's because we're supposed to go up to the nth term. And so what you're going to do is you're going to actually have to use this equation right here to find your nth term. Now, some people, they don't like how big this equation is right here that I've written out. So if you want to simplify it, you can. Take that -8 and distribute it. If you distribute, you will get a little bit of a smaller equation that you might like a little bit more. That would be 5 minus 8n. That's actually your nth term. So that would go right here. It would go 5 minus 8n. This is the first term, this is the last term, this is the number of terms. Now, once again, you might say, well, if I simplified this one up here, can I simplify this one down here? Absolutely, yes, you can. So let's simplify that guy. This guy, if you simplify it down, you can combine these terms together, and then you can start distributing this fraction out in front. And when you do that, the simplified version is n minus 4n squared. That's the simplest version that you can use. So we've simplified both things down pretty well. All right, now what we're going to do right now is we're going to now create another series problem like we had on the front side, and then you are going to get to practice this one out on your own. So what we have is we have our first three terms again, -3, -11, 19, and this is going to go all the way up to the nth term. That's the thing that we found right up here, 5 minus 8n. And if you add up all these terms starting at -3 and ending at 5 minus 8n, it should be equal to n minus 4n squared. See if you can create an induction proof that proves that this sum over here is equal to this small piece of information right here. Try it out, see if you can make that happen for you. All right, good luck. I'll answer any questions that you might have tomorrow.